In the last video, we introduced the concept of torque and used it to solve Newton's second law puzzles. In this video, we will introduce another type of puzzle known as a statics puzzle. A statics puzzle, as its name suggests, is one where nothing is moving. For this to be the case, two conditions must be fulfilled. To prevent any linear acceleration, the force balance has to add up to 0 in all directions, x and y. And to prevent any angular acceleration, the torque balance must also add up to 0. The point of the puzzle is to find the values and positions of the forces so that all the forces and torques cancel out. I'll offer two hints for solving these puzzles. First, to keep the puzzle simple, place the origin in a location where the greatest number of forces pass through. This causes the greatest number of torques to become 0, simplifying the calculations. Second, if an object is made of a uniform material and its shape is regular, the weight force will act at its geometric center. This should make sense to my 103 students from our discussions of center of mass, but it might be new to my 101 students. The simplest example of a statics puzzle is a seesaw. Here is a common puzzle related to seesaws. A 20-kilogram child and a 25-kilogram child are exactly balanced, unmoving, on a 30-kilogram seesaw. The 20-kilogram child is 1.5 meters from the fulcrum, that's the support point. A. What is the normal force on the seesaw from the fulcrum? And B. Where is the second child located? In this question, we have a seesaw, and we have a fulcrum. A fulcrum is the correct name for the support point of a seesaw or of a lever. We have a 20-kilogram child who is at one end of the seesaw, and we have a 25-kilogram child who's on the other end. I am going to set my axes like this. I'm going to set the x-axis to point horizontally, like so. I'm going to set my y-axis to point vertically, like so. Now, let's draw in all of the forces that are applicable here. The 20-kilogram child is going to have their weight force. Remember, these are the forces that are acting on the plank over here. So it's the plank which is feeling those forces. So there's the weight force of the 20-kilogram child. There's the weight force of the 25-kilogram child. There is the weight force of the plank itself. Oh, by the way, we said that the mass of the plank was 30. And finally, there is the normal force which is coming from the fulcrum, the support point. So this is our 20-kilogram child. This is our 25-kilogram child. Now, in order to solve out the distance of the 25-kilogram child to the center of rotation, which is the point of the fulcrum, we need to add up all of these forces and sum them up to 0. And we also need to add up all of the torques and sum those up to 0. One other piece of information that I should have mentioned is that the distance of the 20-kilogram child to the fulcrum is 1.5 meters. So I will put this here in green. Something like that. Now, let us start by setting up the total force for this situation. The total force is given by the normal force pointed up minus the weight of the 20 kilogram child minus the weight of the 25 kilogram child minus the weight of the plank. Okay, now let's solve for what is known over here. Oh, by the way, the total force must be equal to 0. So the weight of the 20 kilogram child is going to be given by mg. That's equal to the mass, that's 20, times g, which is 9.81. That works out to 196.2 newtons. The weight of the 25 kilogram child is 25 times 9.81, which is 245.25. The weight of the 30 kilogram child, the 30 kilogram plank rather, is 30 multiplied by 9.81, which is equal to 294.3. Okay, plugging everything in, we get the normal force minus weight 20, 196.2, weight of the 25, 245.25, weight of the 30, 294.3, is all equal to 0. So the size of the normal force is going to be 196.25. I can basically just add all of these to the other side. So 196.2 plus 245.25 plus 294.3 gives us a syntax error. There, 735.75. And because this is pointed upwards in the positive y direction, we should correctly say 735.75 j hat. All right, so that tells us the force being exerted by the fulcrum on all three of these objects, the two children and the 30 kilogram plank. Cool. The next thing to do is to figure out the torque balance. And to do that, we need to find out what the different torques are. Now, it was strategic that I set my origin to be at the fulcrum. Why? Because that means that the normal force passes through this origin, and the weight force also passes through this origin, which means they exert 0 torque. Anything that passes through the center of rotation always exerts 0 torque. And in this case, because I set my origin to be the center of rotation, I also set it in such a way where 2 of the forces would cancel out. So we only have 2 forces left, which we have to worry about the torques for. So let's start off by finding out how big those torques are. What is the torque of the 20 Newton? Or the 20 kilogram child? So the torque of 20 is equal to the distance of the 20 kilogram child to the center of rotation, that's the lever arm, multiplied by the force that's being exerted there, that would be the weight of the 20 kilogram child, multiplied by the sine of the angle between them. So that's going to work out to the distance, 1.5, times the force. The weight of the 20 kilogram child was 196.2, times the sine of the angle between them. So the lever arm looks something like this. Curl our fingers down, that would give us the direction of the weight force. That's a 90-degree angle over there. So from the lever arm to the weight force, that's 90 degrees. So that gives us that the torque of the 20 kilogram child is going to be 1.5 times 196.2 times sine of 90 is 1, so that gives us 294.3. This would be in Newton meters, or Newton's times meters, rather. And we can also see that this is a counterclockwise torque, which you can confirm using the right-hand rule. Lever arm, left. Force, down. Torque, positive, out of the page. So we could write this as 294.3 k hat Newtons times meters. Now, we can do something similar for the torque of the 25 kilogram child. That's going to work out to the distance that's unknown. Let's just call that x for the moment, or maybe to prevent any confusion, let's call it R25. Times the force that this 25 kilogram child is exerting, that's the weight force, 245.25, times the sine of the angle between them. So that means the lever arm is pointing rightwards, the force is pointing downwards, that's 90 degrees. Okay, so that means that the torque of the 25 kilogram child is equal to R25, unknown, but 245.25, sine of 90 is 1, so that works out to 245.25 multiplied by the unknown radius multiplied by, and that would be in Newton's times meters. Now, what would be the direction of this torque? Well, rightwards is positive. Rightwards for the lever arm, downwards for the force. That corresponds to a force pointing into the page. Or for my 101 students, this is a force that would cause clockwise motion. So correctly, this should be negative 245.25 times R25 time, and that would be in k hat. Finally, we have all of this information. We are ready to apply the torque balance. The total torque is equal to the 20 kilogram child minus the torque of the 25 kilogram child, because that's a negative torque. All of that's equal to 0. Plug everything in. 294.3 minus 245.25 times the distance of the second child to the fulcrum is going to give you 0. So, rearranging this a little bit, we get 294.3 is equal to 245.25 times that distance. So 294.3 divided by 245.25 gives us 1.2. So the distance of the heavier child to the fulcrum is only 1.2 meters. The heavier child is closer to the fulcrum than the lighter child. So let's do a quick review of how we solved this question. First, we solved for the force balance. We worked out what all of the forces were. Here is the weight of the 20 kilogram, the weight of the 25 kilogram child, and here is the weight of the plank. And we could solve for the normal force. Then we solved for the torque being exerted by the 20 kilogram child and the torque being exerted by the 25 kilogram child. And we can put those together and we can solve for how far away the 25 kilogram child must be away from the fulcrum. And this makes sense because the 20 kilogram child has a smaller weight than the 25 kilogram child. To balance this out, the 25 kilogram child has to have a shorter lever arm than the 20 kilogram child. Here's a similar puzzle. A 4-meter, 60-kilogram scaffold is suspended by 2 ropes. The ropes are attached to each end of the scaffold. A 10-kilogram cat sits 1 meter from the left end of the scaffold. What are the tensions in the 2 ropes? In this question, we have a scaffold, and it is supported on 2 ropes. On one side of the scaffold, there is a cat. Now, I'm going to set my axes. That's my x-axis, and here is my y-axis. Next, let's write in the information that we know about the cat and the scaffold. We know that the scaffold has a mass of 60, and the cat has a mass of 10 kilograms each. There are 4 forces that we need to worry about. There's the weight of the scaffold. There is the tension in each of the 2 ropes. So I'm going to call this one T1, and I'm going to call this one T2. Finally, there is the weight of the cat. Now, the last piece of information that we need. The length of the scaffold is 4 meters. So that means that this point of the scaffold is 2 meters. This point of the scaffold will be negative 2 meters. And the position of the cat is 1 meter to the left of the center point. So now we have all of the information that we need to solve this question. So let's go ahead and do that. The first thing that we need is a force balance. So the force balance would look something like this. The sum of the forces would be equal to the tension 1, pointed up, plus tension 2, also pointed up, minus the weight of the scaffold, which is pointed down, minus the weight of the cat, which is also pointed down. And all of that's equal to 0. Now, let us solve for what we know. Let's start with the weight of the scaffold. The weight of the scaffold is given by mg, which would be equal to 60 times 9.81, which equals, I don't know that off the top of my head, 60 times 9.81 is 588.6. The weight of the cat is also given by mg, that would be 10 kilograms times 9.81, which works out to 98.1 newtons. So now, let's substitute everything that we know into the force balance. T1 is unknown, plus T2, also unknown, minus weight of the scaffold, that's 588.6, minus weight of the cat, which is 98.1. All of that's equal to 0. So now all we have to do is move these two numbers and add them to the other side. 588.6 plus 98.1 gives us 686.7. So we can write this as tension 1 plus tension 2 equals 686.7. So that is the result that we have gotten by solving the force balance. Now we are ready to turn to the torque balance. Let's start by looking at the torque which is being caused by tension 1 around this center point. Actually, there are 3 different torques we need to examine. The one from tension 1, the one from tension 2, and the one from the weight of the cat. The weight of the scaffold passes through our origin, which means that its lever arm is 0, which means that its torque is also 0. So, let's solve for the torque being caused by tension 1. The torque, let's call this torque 1, is equal to the lever arm, R, multiplied by the size of the force, F, times the sine of the angle between them. Let's continue. That's going to be equal to the distance from the center point, from our origin to the point where the force is being applied, that's 2 meters, times the size of the force, tension 1, times the sine of the angle between them. Here the lever arm is pointed leftwards, the tension is pointed upwards, that's 90 degrees. Sine 90 is 1, so this whole thing works out to 2 multiplied by T1. Now, next point. Is this a clockwise negative torque, or is it a counterclockwise positive torque? Well, if we imagine the center of rotation being here, this torque is going to move it in this direction. That is clockwise. It's a negative torque. So torque 1 works out to be negative. And now we can proceed to torque 2. Torque 2 is going to be given by the lever arm here is 2 meters. The size of torque 2 is unknown, times the sine of 90 degrees. So sine of 90 is 1, 2 times 1 is 2, so that gives us 2 times T2. So that gives us the torque from the second tension. Okay, and finally, the torque from the cat. Oh, by the way, the torque from the second tension will be positive. We know this because if we put this as our center of rotation, this force will tend to rotate this counterclockwise. That's the positive direction. Now, as for the cat, the distance from the cat to the center of rotation is 1 meter, times the weight of the cat, that was 98.1, times the sine of the angle between the force and the lever arm. Lever arm points left, force points down. That's going to be sine of 90. So 1 times 98.1 times sine of 90, which is also 1, gives us a torque of 98.1. And this torque is going to be counterclockwise, so it's positive. This is now the third torque that we need for this torque balance. And now we're ready to do the torque balance. So, like I said, there are 3 torques. The total torque is equal to the positive torque from T2, let's call that T2, like this, plus the positive torque of the cat minus the negative clockwise torque of T1. And all of that is equal to 0. So, let us substitute for what we know. Torque 2 is equal to 2 multiplied by tension 2. Plus the torque of the cat, that's 98.1, is equal to, I'm going to move this to the other side, torque of the first tension. Because I move it to the other side, it becomes positive. So this becomes 2 times T1, like that. Let's simplify this. Divide everything by 2. I end up with tension 2 plus half of 98.1 is 49.05 equals tension 1. Okay, so that's as simple as we can make this. We now have one relationship between the tensions thanks to the torque balance, and a second relationship of the tensions due to the force balance. Now all we have to do is plug one into the other and we can solve for the two tensions. So let's go ahead and do that. T1 is equal to T2 plus 49.05, so let's plug that in here. So I'm going to write this as T2 plus 49.05 plus T2 is equal to 686.7. So this statement over here has come because I substituted this equation into this equation, like that. We can simplify this. T2 plus T2 gives us 2 times T2. And the 49.05 can be moved to the other side. So we now have 686.7 minus 49.05 gives us 637.65. So T2 is going to be equal to half of that. That's 318.825. Since T1 and T2 add together to give us 686.7, that means that T1 must be equal to 686.7 minus 318.825, which is 367.875. So that's our answer. We have now solved for the tensions in the two ropes. And what we see is that the second rope, the one which is on the right, has a lower tension than the one which is on the left. And that makes sense because you expect the tension in the left rope to be greater because the cat is sitting closer to the left rope. The left rope has to have a greater tension to support the closer weight of the cat. In this video, we introduced statics puzzles in one dimension. In the next video, we will explore statics puzzles in two dimensions.